The sky has always been predictable. For thousands of years, we have watched the heavens turn with clockwork precision, tracking planets along their elliptical paths, charting stars as they wheel through the seasons, and marking comets as they sweep through the inner solar system in great arcs of ice and light. We have built our understanding of the cosmos on the foundation of these regularities, on the laws that govern motion and mass, gravity and light. We know what comets should do because we have seen them do it countless times. They arrive from the dark outer reaches, carrying pristine ice from the formation of the solar system itself, and as they approach the sun, they begin to wake. Solar radiation strikes their frozen surfaces, warming them, causing volatiles to sublimate directly from solid to gas. This outgassing creates the characteristic coma, the glowing envelope of gas and dust that surrounds the nucleus, and it gives birth to the tail, that magnificent streamer that can stretch for millions of kilometers across space. The physics is straightforward. Solar wind, that constant stream of charged particles flowing outward from the sun at hundreds of kilometers per second, pushes against the gas and dust released by the comet. The pressure is gentle but relentless, and it shapes the tail into a structure that always points away from the sun, regardless of the comet's direction of travel. This is not a wake trailing behind a moving object, not like water streaming behind a boat. Instead, it is a phenomenon entirely dictated by the geometry of sunlight and solar wind. A comet approaching the sun has its tail streaming behind it. A comet departing has its tail streaming ahead, leading the way like a banner. The tail does not follow the path of motion, but rather the direction of force, and that force always originates from our star. This behavior is so consistent that it serves as one of the fundamental teaching examples in astronomy. Students learn it in their first courses. Observers expect it. Modelers build simulations around it. When a new comet is discovered, teams of astronomers can predict with remarkable accuracy what it will do, how bright it will become, when it will be visible, and how its tail will develop. There are variations, of course. Some comets are more active than others. Some have complex rotation states that cause jets of gas to erupt from specific locations on their surfaces. Some fragment under the stress of solar heating or tidal forces. But these variations occur within well-understood parameters. They are the expected deviations, the natural chaos that arises from irregular shapes and heterogeneous compositions. Comets are, fundamentally, passive objects. They do not choose their paths. They do not control their behavior. They are ancient chunks of ice and rock, remnants from the primordial disk that formed our planets, and they respond to forces the way any inert mass must respond. Gravity pulls them. Radiation pushes their ejecta. Rotation tumbles them. Nothing about a comet suggests intention or design. They are beautiful, yes, and scientifically invaluable, but they are also profoundly simple in their nature. They are debris, wanderers, messengers from the deep past. They are not supposed to surprise us. And then came 3I/Atlas. The designation itself marks it as unusual. The prefix 3I indicates the third confirmed interstellar object detected passing through our solar system. The first was 1I/Oumuamua, discovered in 2017, an elongated body that tumbled through the inner system and departed without ever developing a tail, leading to years of debate about its composition and nature. The second was 2I/Borisov, identified in 2019, a more conventional comet that behaved largely as expected, reassuring astronomers that not every interstellar visitor would rewrite the textbooks. 3I/Atlas was detected early in its approach, flagged by automated survey systems scanning for near-Earth objects and potential hazards. Initial observations suggested it was unremarkable, another icy body on a hyperbolic trajectory that would swing past the sun and depart back into the depths of interstellar space. Telescopes around the world turned toward it. Spectrographs began capturing its light, breaking it into component wavelengths to identify the elements and molecules present in its coma. Imaging systems tracked its position night after night, refining calculations of its orbit. Photometric monitoring recorded its brightness over time, searching for the periodic variations that would reveal its rotation rate. And in those early weeks, 3I/Atlas seemed to conform to expectations. It was developing a coma. It was brightening slowly as it approached the sun. Its spectral signatures showed the characteristic features of water ice and simple carbon compounds. Everything fit. But then observers began to notice something peculiar. In images taken with large telescopes, a secondary structure became visible. It was faint at first, easy to dismiss as an artifact of image processing or a foreground star captured in the same frame. But as more observatories confirmed it, the reality became undeniable. There was a second tail. Unlike the primary tail, which streamed away from the sun in the expected direction, this new structure extended in the opposite direction, pointing back toward the sun. It was quickly termed an anti-tail, a designation borrowed from rare but not unheard of observations in comet astronomy. Anti-tails have been observed before, most famously in historical comets like Roland in 1957. They are generally understood as optical illusions, perspective effects that occur when Earth's viewing angle passes through the plane of a comet's dust tail. From certain geometries, the broad fan of dust particles can appear to extend toward the sun, even though no material is actually moving in that direction. The particles are still being pushed outward, but the projection creates the illusion of a sunward spike. Experienced astronomers recognized the phenomenon, and many initially assumed that 3I/Atlas was simply providing another textbook example of this geometric effect. But as observations accumulated, the perspective explanation began to fail. The anti-tail was not behaving as a projection artifact should. For one, it persisted far longer than any geometric alignment would allow. As Earth moved along its orbit, changing the viewing angle week by week, the anti-tail remained visible and coherent. It did not fade or disappear as the geometry shifted. Instead, it seemed to be a physical structure, a real concentration of material extending from the nucleus in a direction that should have been impossible. Measurements of its length were even more startling. Using careful astrometry and distance corrections, researchers calculated that the anti-tail extended more than 400,000 kilometers from the comet's nucleus. To put this in perspective, the average distance from Earth to the Moon is roughly 384,000 kilometers. This structure was longer than the span between our planet and its closest celestial neighbor. No perspective illusion could create an apparent feature of such magnitude, especially one that remained stable over such extended observation periods. The physics of this presented an immediate problem. In order for material to extend sunward from a comet's nucleus, it would have to be moving against the solar wind and radiation pressure. This would require the particles to have been ejected with tremendous velocity, far greater than the gentle outgassing forces typically observed. And even if such a violent ejection had occurred, the material would quickly be decelerated and swept backward by the relentless pressure of solar radiation. There was no known mechanism that could sustain a sunward tail of this size for more than a brief moment, yet 3I/Atlas was maintaining it day after day. Some researchers proposed that the anti-tail might consist of unusually large dust grains, particles massive enough that radiation pressure would have less effect on them, allowing them to coast further sunward after ejection. But this theory required exceptionally specific grain sizes and ejection velocities, and it still failed to explain how such a narrow, coherent stream could be maintained. Others suggested complex rotation states or precession effects that might create asymmetric jets, but modeling efforts could not reproduce anything close to what was being observed. And then came the second discovery, one that would make every attempt at conventional explanation seem hopelessly inadequate. The anti-tail was not static. It was not simply extending sunward in a fixed configuration. It was moving. Specifically, it was wobbling. High-cadence imaging campaigns, using large ground-based telescopes equipped with adaptive optics to compensate for atmospheric distortion, revealed that the anti-tail underwent regular oscillations. The structure would shift slightly back and forth, not in a random or chaotic manner, but with clear periodicity. The tip of the anti-tail traced a small but measurable path across the sky, swaying with rhythmic precision. This was unprecedented. Material in a comet's tail can show variations due to changes in outgassing rate or rotation-induced jets, but those variations are either irregular or directly tied to the nucleus's rotation period. The wobble observed in 3I/Atlas's anti-tail had a period that was entirely independent of the object's rotation. Photometric analysis had determined that the nucleus rotated approximately once every 8.2 hours, a value consistent with other comets of similar size. But the anti-tail wobble had a different rhythm entirely, cycling with its own distinct frequency. The implications of this were profound. For a structure to oscillate independently of the parent body's rotation meant that something other than simple spin dynamics was at work. There had to be a force being applied, a transfer of momentum that was not tied to the nucleus's tumbling motion. In engineering terms, this looked like active control. It resembled the behavior of a system that was being adjusted, corrected, stabilized by deliberate input. Consider what it would take to make such a structure wobble. If the anti-tail were composed of passive dust and gas, there would be no mechanism to create organized oscillation. Particles ejected from a rotating nucleus might create spiral patterns or time-variable fans, but those would be locked to the rotation period. Solar wind variations might cause the primary tail to flutter or ripple, but the solar wind is turbulent and irregular. It does not produce steady, periodic effects. Magnetic field interactions might come into play if the comet were shedding significant amounts of ionized material, but even those interactions would be expected to create irregular disturbances, not the metronomic regularity being observed. The frequency of the wobble remained stable over weeks of observation. It did not drift or decay. It did not show the kind of chaotic variation expected from natural turbulence. Instead, it maintained a precision that seemed almost artificial. Researchers began using terms like coherent oscillation and phase-locked behavior, language borrowed from signal processing and control systems engineering rather than traditional comet science. To create such behavior intentionally would require a mechanism capable of exerting force in a controlled manner. It would need a way to push against the surrounding space, to generate thrust or torque in specific directions at specific times. In terrestrial engineering, we accomplish this with jets, with control thrusters, with reaction wheels, and gyroscopes. Spacecraft maintain their orientation and adjust their trajectories using these tools, firing tiny bursts of propellant to create the forces needed for maneuvering. The wobble of the anti-tail looked disturbingly similar to a wake pattern, the kind of disturbance left behind by a vessel making small course corrections as it travels. Submarines, for instance, constantly adjust their control surfaces and propulsion to maintain depth and heading, and these corrections create subtle but detectable disturbances in the surrounding water. Aircraft trim their control surfaces in flight, making continuous micro-adjustments that keep them stable despite air turbulence. What was being observed in 3I/Atlas had the signature of active stabilization, of a system responding to perturbations and correcting them in real time. This interpretation was unsettling enough that many researchers hesitated to state it plainly in their papers. Academic caution and the culture of peer review discourage speculative leaps, especially ones that invoke language associated with artificial systems. Papers were carefully worded to describe the observations as anomalous or unexplained, noting that conventional comet models do not currently account for this behavior, without directly stating what the implications might be. But the observations continued to accumulate, and each new data set made conventional explanations less tenable. Spectroscopic analysis, in particular, began to reveal details that were difficult to reconcile with natural comet composition. When we observe a comet spectroscopically, we collect its light and pass it through a diffraction, grating, or prism, spreading the light into a spectrum from ultraviolet through visible and into infrared wavelengths. This spectrum is not smooth. It contains dark absorption lines and bright emission lines at specific wavelengths, each corresponding to a particular element or molecule. By analyzing these features, we can determine what the comet is made of, what gases are vaporizing from its surface, and what dust particles are scattering its light. For a typical comet, especially one originating from the outer solar system or interstellar space, the spectral signatures are predictable. We expect to see strong emission from water, which is by far the most abundant volatile in cometary ice. We expect carbon dioxide, carbon monoxide, methane, ammonia, and various simple organic compounds. We expect to see traces of rock-forming elements like silicon and magnesium in the dust, but these are generally in solid form, reflecting light rather than emitting it. The spectra of 3 I/Atlas showed the expected water and simple volatiles, but they also showed something else, something that should not have been there. There were emission lines corresponding to metallic elements, iron, nickel, and magnesium, all appearing in ionized states. The presence of these elements was not the anomaly. Comets do contain trace amounts of metals embedded in their dust grains. What was anomalous was that these metals were appearing as emission lines, meaning they were hot enough and energetic enough to be glowing, to be emitting light at specific wavelengths. This requires temperatures and energy densities far beyond what natural solar heating can produce in a comet's coma. Iron, for instance, has ionization lines that appear in the visible spectrum when the atoms are stripped of electrons by high-energy collisions or intense ultraviolet radiation. To see strong emission from ionized iron in a comet's coma would require either extreme temperatures, far hotter than anything solar radiation could create at these distances, or very high densities of energetic particles. Neither condition is met in a normal comet. Nickel presented a similar puzzle. Its emission lines were clear and unambiguous, indicating that nickel atoms were not only present, but actively excited, emitting photons as their electrons dropped back to lower energy states after being energized. This is the behavior of a plasma, a state of matter where electrons are stripped from atoms and the resulting ions and free electrons interact in complex, high-energy ways. Magnesium, too, showed emission features that suggested high temperatures and ionization. The strength and width of these emission lines indicated that the metallic plasma was not just a trace contaminant or a minor component. It was a significant and stable feature of the coma, one that persisted across multiple observations. The spectral signatures were strong, concentrated along the axis of the anti-tail. When observers compared spectra taken from different regions of the coma, the metallic emission was most intense near the base of the anti-tail structure, weakening toward the sides and rear. This spatial correlation suggested that whatever was producing the metallic plasma was directly associated with the anti-tail itself. The natural interpretation, the one that would fit within conventional comet science, would be that the comet had an unusually high metal content in its dust, and that somehow this dust was being heated or excited. But the temperatures required were simply not available. Solar ultraviolet radiation at the comet's distance could not ionize metals efficiently. Collisions between gas molecules in the coma are too gentle and infrequent to produce the necessary energies. There was no credible natural heat source that could explain what was being observed, unless the heat source was internal. This was the conclusion that some researchers began to entertain, cautiously at first, then with growing confidence as alternative explanations failed. If the metallic emission was not being produced by external solar heating, then it had to be coming from energy released within the object itself. and the characteristics of the emission looked remarkably similar to something well known in aerospace engineering: ionized exhaust. Plasma propulsion systems, both those currently in experimental development and those theorized for future deep space missions, work by ionizing a propellant, often a noble gas like xenon or a metal like cesium, and then accelerating the ions to extremely high velocities using electric or magnetic fields. The exhaust stream from such a system is a glowing plasma, rich in ionized metals and emitting strongly at characteristic wavelengths. The emission spectrum of a plasma thruster depends on the propellant used and the energy of the acceleration, but it invariably includes strong metallic emission lines. The spectral signatures from 3I/Atlas bore a striking resemblance to the exhaust plumes documented in laboratory tests of ion drives and Hall-effect thrusters. The presence of iron and nickel was particularly suggestive, as these elements have been studied as potential propellants for certain types of electromagnetic propulsion systems. Magnesium, too, has been considered for its favorable ionization properties and relatively high abundance in certain mineral compositions. If the anti-tail were an exhaust plume, it would explain not only the spectral anomalies but also the physical structure and behavior. A directed plasma jet would naturally create a narrow, elongated feature extending from the source. It would glow visibly due to the excited ions emitting light. And if the thrust were being modulated, turned on and off or varied in intensity, it would create exactly the kind of wobble being observed, as the momentum imparted by the exhaust created oscillations in the object's trajectory or orientation. To sustain such a plume would require magnetic containment, a way to shape and direct the plasma without it dispersing immediately into the surrounding space. Plasmas are notoriously difficult to control because the charged particles interact with magnetic fields and with each other in complex ways. In fusion reactors, magnetic confinement is achieved using powerful superconducting magnets arranged in carefully designed geometries. In plasma thrusters, magnetic fields channel the ions through an acceleration stage and out the exhaust nozzle. The anti-tail's coherence and length suggested that some form of magnetic structuring was at work. The plume extended for hundreds of thousands of kilometers without dispersing significantly, maintaining a relatively narrow profile. This would be impossible without some mechanism to prevent the plasma from expanding laterally. Magnetic fields aligned along the plume's axis could provide this confinement, creating a kind of invisible channel that guided the ion sunward. Such a field structure would also explain why the plume appeared to oscillate as a coherent unit rather than breaking up into turbulent eddies. Magnetically confined plasmas can support wave-like perturbations, organized oscillations that travel along field lines. If the magnetic field itself were being modulated, either in strength or geometry, it could drive the wobble behavior directly. All of this pointed toward active energy use, toward systems that were not just passively responding to solar heating, but actively generating and directing energy for specific purposes. The amount of power required to ionize and accelerate metals, to maintain magnetic confinement over such distances, and to do so continuously for weeks on end would be substantial, likely on the order of megawatts. And then there was the density problem. As observational campaigns continued, refinements to the orbit allowed increasingly precise estimates of the object's mass. By measuring the tiny gravitational perturbations exerted on nearby spacecraft, though none were close enough for direct measurement, and by analyzing the non-gravitational accelerations caused by outgassing, researchers could place bounds on the nucleus's mass. Combined with high-resolution imaging that estimated the nucleus's size and shape, this allowed calculation of bulk density. The numbers that emerged were startling. The estimated density of 3I/Atlas was somewhere between 0.1 and 0.3 grams per cubic centimeter. To contextualize this, water ice has a density of about 0.9 grams per cubic centimeter. Rock is typically between 2 and 3 grams per cubic centimeter. Even highly porous materials like aerogel or pumice rarely drop below 0.5 grams per cubic centimeter while still maintaining structural integrity. A density of 0.1 to 0.3 grams per cubic centimeter is less than ice. It is barely denser than certain types of foam. For a body several hundred meters across, this was almost incomprehensible. How could such an object hold together? What could it be made of? Natural explanations were attempted. Perhaps the nucleus was extraordinarily porous, a loose rubble pile of icy fragments barely clinging together through weak gravity. But such a structure would be expected to be highly irregular and prone to fragmentation, especially under the stresses of rotation and outgassing. High-resolution images, however, showed a relatively smooth, cohesive shape without obvious signs of active disintegration. Another possibility was that the nucleus was composed of some exotic low-density ice, perhaps rich in volatiles like nitrogen or methane that had remained frozen during the object's interstellar journey. But even the lightest ices do not approach these density values, and spectroscopy had already confirmed that water was the dominant volatile, not lighter compounds. The most straightforward explanation for such low density was also the most provocative. The object was hollow. Not naturally hollow, like a geode formed by geological processes, but hollow in the sense of having large internal voids, empty spaces that reduced the overall mass relative to volume. This is precisely how spacecraft are designed. Launch vehicles, satellites, space stations, all are hollow structures with thin walls and empty interior spaces. They have to be, because carrying unnecessary mass into space is prohibitively expensive in terms of fuel and structural load. A hollow structure would also explain the object's surprising stability. A solid body with such low density would likely be mechanically weak, prone to crumbling or deforming. But a hollow shell, especially one with internal bracing or compartmentalization, can be quite strong. Engineering designs for large spacecraft, including concepts for interstellar probes, invariably feature hollow configurations with structural members arranged to maximize strength while minimizing mass. If 3I/Atlas were an engineered structure, its density would make perfect sense. The outer shell would need to be thick enough to provide thermal insulation and protection from micrometeoroids during the long interstellar journey. But the interior could be largely empty or filled with lightweight systems and fuel tanks. The overall density would naturally fall into the range being observed. This interpretation meshed disturbingly well with the other anomalies. A hollow craft could house power systems, propulsion units, and control mechanisms. It could store fuel or propellant for the plasma exhaust. It could contain the magnetic field generators needed to shape and direct the plume. Everything fit. But there was more, another layer of strangeness that compounded the mystery. The object's brightness was behaving in ways that defied conventional comet behavior. Normally, as a comet approaches the sun, it brightens. This is intuitive and well documented. Increased solar heating causes more vigorous outgassing, expanding the coma and increasing the amount of dust and gas that scatters sunlight. The relationship is predictable enough that astronomers can forecast a comet's peak brightness months in advance based on its orbit and estimated size. 3I/Atlas was not following this pattern. It had brightened initially as expected during its approach, but as it drew closer to the sun and should have been reaching peak activity, it began to dim instead. This was gradual at first, easy to attribute to natural variations in activity or dust production. But the trend continued, and photometric measurements confirmed that the object was becoming significantly fainter, even as its distance from the sun decreased. At the same time, measurements of the object's albedo, the fraction of sunlight it reflected back into space, yielded surprisingly low values. Albedo is expressed as a number between 0 and 1, where 0 represents a perfectly black surface that absorbs all light, and 1 represents a perfectly reflective surface. Fresh ice has an albedo of around 0.6 to 0.7, meaning it reflects 60 to 70% of the sunlight hitting it. Rocky surfaces vary widely, but typical asteroids have albedos in the range of 0.1 to 0.3. 3. I/Atlas had an estimated albedo below 0.1, meaning it reflected less than 10% of incoming sunlight. Some measurements suggested it might be even lower, approaching 0.03 or 0.04. This meant the object was absorbing more than 97% of the sunlight striking its surface. Such low albedos are rare in the solar system. The darkest surfaces known, found on certain carbonaceous asteroids and the surface of Saturn's moon Iapetus, have albedos around 0.02 to 0.05. These surfaces are so dark because they are coated in complex carbon compounds or organic tholins that absorb light extremely efficiently. But even those dark materials typically brighten significantly when covered in dust or ice, and a comet shedding gas and dust should not be developing an increasingly dark surface. If anything, the exposure of fresh ice from the interior, as layers sublimate, should increase reflectivity, not decrease it. There are two general reasons why an object might be engineered to absorb light so efficiently. The first is stealth, the desire to minimize visibility. In space, where there is no atmosphere to scatter light and create contrast, a dark object against the darkness of space is extremely difficult to detect unless it passes in front of a bright background. Military reconnaissance satellites and certain experimental spacecraft have been coated with highly absorptive materials specifically to reduce their radar and optical cross-sections, making them harder to track. The second reason is energy collection. Solar panels, for instance, are designed to absorb as much sunlight as possible and convert it into electrical energy. The best photovoltaic materials are visually dark because they are not reflecting light away. They are capturing it. An interstellar probe operating on solar power would benefit enormously from a high-efficiency energy collection system, and maximizing absorption would be a key design goal. The timing of the dimming was significant. 3. I/Atlas began to darken most noticeably as it reached the region of peak solar flux, the point in its trajectory where the intensity of sunlight was greatest. If the object were harvesting solar energy, this would be the optimal time to do so, collecting as much power as possible before departing back into the cold outer system and eventually interstellar space. The wobbling anti-tail, if it were indeed an exhaust plume, might function partly as a solar or magnetic sail during this phase, capturing momentum from solar wind and radiation while the primary energy systems charged or activated. The correlation was tantalizing. An object darkening precisely when solar energy was most abundant, while simultaneously displaying signs of active propulsion and high energy emissions, suggested a coordinated system coming online. It looked like a spacecraft transitioning from cruise mode to active operations, deploying systems that had been dormant during the long interstellar crossing and beginning to execute mission objectives. And then came the light curve anomalies, observations that pushed the mystery into even stranger territory. Amateur astronomers, equipped with moderately sized telescopes and sensitive CCD cameras, contribute enormous amounts of data to comet observation campaigns. Their continuous monitoring provides temporal coverage that professional observatories, with their limited time allocations and diverse research priorities, cannot match. It was a network of these amateur observers who first detected the periodic brightness drops in 3I/Atlas. The drops were small but unmistakable. Every 144 minutes, the object's brightness would decrease by a precise amount, approximately 0.4 magnitudes. In the logarithmic scale used to measure brightness in astronomy, a change of 0.4 magnitudes corresponds to a reduction of about 32% in the amount of light reaching the observer. The drop would last for several minutes. Then the brightness would return to its baseline level, only to drop again 144 minutes later. The regularity was extraordinary. Natural variations in comet brightness due to rotation, outgassing jets, or dust clouds are irregular and unpredictable. Even if a rotating nucleus had a particularly active region that faced Earth at intervals, the timing would be tied to the rotation period, and any periodicity would drift as the rotation state evolved. But the 144-minute cycle held with mechanical precision over weeks of observation. It did not drift. It did not vary. It repeated with the accuracy of a clock. The magnitude of the drop was also exactly consistent, not varying by more than a few percent from event to event. This was not the behavior of a chaotic dust cloud passing in front of the nucleus. It was the signature of something structured, something with a fixed geometry and a regular motion. To create such precise brightness variations would require a mechanism that could predictably block or redirect light. In astronomical contexts, this is usually achieved by transits, when one object passes in front of another from the observer's perspective. Exoplanets are detected by the tiny dips in their host star's brightness as the planet crosses the stellar disk. Eclipsing binary stars show regular brightness variations as each star passes in front of its companion. But 3I/Atlas was not a binary system, and there was no companion object that could be transiting in front of it. The brightness drops had to be caused by something associated with the object itself. The most straightforward explanation was that something was periodically occulting the nucleus, blocking the light from reaching Earth at regular intervals. What could serve this function? In an engineered system, the possibilities were numerous. A rotating structure, a shutter, a panel, a sail, any component that moved in a regular cycle and periodically blocked the line of sight. The 144-minute period suggested a rotation or oscillation distinct from the nucleus's own 8.2-hour spin. Perhaps an external component, a boom or antenna or array, rotating independently of the main body. The precision of the timing suggested active control. Passive mechanical systems, like a freely spinning object, might maintain periodic behavior for a time, but friction, however slight, or tidal forces, or outgassing jets, would cause the period to drift gradually. The 144-minute cycle showed no such drift, implying that whatever was causing the occultation was either driven by an active mechanism or so perfectly balanced and isolated from perturbations that it maintained absolute regularity. Some researchers began to examine the light curve data more closely, looking for fine structure within the brightness drops. What they found was even more intriguing. The drops were not simple square pulses, instant decreases followed by instant recoveries. Instead, there was subtle structure, slight variations in the depth and duration of each event. The timing between events also showed minute variations, deviations of a few seconds or tens of seconds from the average 144 minutes. These variations were not random. When analyzed statistically, they appeared to contain patterns, correlations that suggested structure rather than noise. The variations in timing could be interpreted as modulation, changes in the interval between pulses that might encode information. This is the basis of pulse position modulation, a technique used in digital communications where information is encoded in the timing between events rather than in the events themselves. Similarly, the variations in the depth of the brightness drops could represent amplitude modulation, where the strength of a signal carries information. Together, these variations hinted at the possibility of a modulated signal, a stream of data being transmitted using the brightness variations as a carrier. The idea was speculative, and many researchers were reluctant to state it explicitly, but the mathematics were compelling. The pattern of brightness variations, when subjected to Fourier analysis and information theory metrics, showed characteristics inconsistent with random noise and more consistent with structured data. The bit rate, if it were indeed a signal, would be extremely low, only a few bits per hour, but for a transmission intended to propagate across interstellar distances, low data rates are expected. Long-distance communication requires high power and long integration times to overcome noise, and a slow, highly redundant signal might be the only feasible approach. What made this possibility even more striking was the directional alignment of the anti-tail. While the primary tail pointed away from the sun as expected, and the anti-tail pointed sunward, the anti-tail's orientation was not exactly radial. Careful astrometry revealed that it deviated by approximately 12 degrees from the direct sun-comet line. This deviation was consistent and stable, not fluctuating with outgassing or rotation. For a passive dust or gas structure, any deviation from radial alignment would require a specific set of conditions. Dust grains could be pushed slightly off-axis by radiation pressure if they had asymmetric optical properties or if the comet's outgassing jets were angled. But the degree of deviation and its stability were difficult to reconcile with these mechanisms, especially given the anti-tail's enormous length and coherence. The direction of the deviation was revealing. When the trajectory of the comet was analyzed and its incoming path traced backward, it pointed toward a region of the sky near the galactic center, the dense core of the Milky Way where hundreds of billions of stars cluster within a relatively compact volume. The anti-tail's 12-degree offset aligned it almost precisely with this direction, pointing back toward the region from which the object had come. This was difficult to explain as coincidence. If the anti-tail were a natural structure, there would be no reason for it to preferentially align with the comet's origin point. The forces acting on it, solar wind and radiation, have nothing to do with the object's history or trajectory. But if the anti-tail were an artificial structure, a communications array or directed transmission system, then such alignment would be entirely logical. Consider how humanity communicates with distant spacecraft. The Voyager probes, now in interstellar space, must aim their high-gain antennas at Earth with extreme precision in order to transmit their faint signals across billions of kilometers. The geometry is critical. A few degrees of misalignment and the signal is lost, dispersed into the vastness of space rather than focused on the receiver. Long-distance communication across interstellar voids would require even greater precision and power, and the transmitter would need to point directly at the intended recipient. If 3I/Atlas were transmitting data back toward its origin, the anti-tail's alignment made perfect sense. It would serve as a directional antenna, a structure designed to focus energy or modulated radiation in a specific direction. The wobble behavior, the periodic oscillations that had seemed so anomalous, could represent fine adjustments in the pointing direction, small corrections to keep the transmission aligned despite the object's motion and the accumulated perturbations of its long journey. The brightness variations could be the signal itself, encoded in changes in the intensity of light or other radiation emitted along the axis of the anti-tail. From Earth's perspective, situated almost perpendicular to the transmission axis, we would be seeing only scattered or reflected light from the edges of the beam, but the periodic changes in geometry as the structure wobbled might cause regular variations in how much of that light reached us. This interpretation transformed the object from a passive visitor into an active participant, an emissary not merely passing through but executing a mission. And the timeline of its activity suggested that the mission was approaching a critical phase. December 19th was marked on calendars across the astronomical community, not because of any announcement or predicted event, but because the geometry of the solar system on that date created a unique configuration. On that day, Earth would pass through a precise alignment between 3I/Atlas and the Sun, reaching a position where the three bodies formed a nearly perfect straight line. Such alignments occur regularly for solar system objects and are usually of interest mainly for occultation observations or gravitational lensing experiments. But in the context of 3I/Atlas and its increasingly strange behavior, December 19th took on a different significance. From a communications standpoint, the alignment created an optimal transmission window, During the hours when Earth was positioned between the object and the Sun, the geometry would minimize certain types of interference and noise. The Sun is an intense source of radio waves, charged particles, and electromagnetic radiation across a broad spectrum. For a signal trying to propagate sunward from beyond Earth's orbit, the Sun's emissions would normally create a high level of background noise, making it difficult to detect weak signals. But when Earth is positioned between the transmitter and the Sun, our planet effectively blocks some of that solar noise, creating a temporary radio shadow where sensitive receivers might detect signals that would otherwise be overwhelmed. Additionally, Earth's gravity creates a slight lensing effect on electromagnetic radiation passing nearby. While the effect is far too small to focus light the way a glass lens does, it can cause measurable phase shifts and amplitude changes in radio signals, effects that could be exploited for enhanced communication under the right circumstances. Advanced communication systems might be designed to take advantage of such geometric configurations, timing transmissions to occur when natural alignments provide small but significant improvements in signal-to-noise ratio. The window would be brief. Earth's orbital motion would carry it through the alignment in a matter of hours, perhaps 4 to 6 hours where the geometry was optimal. If 3I/Atlas were operating on a pre-planned mission timeline, and if December 19th had been calculated in advance as a key communication opportunity, then the object's systems would need to be ready, powered up, and operational by that date. This brought renewed attention to the wobble frequency changes that had been observed in recent weeks. The oscillation period of the anti-tail had not remained constant. Initially measured at 8.2 hours per cycle, matching the nucleus's rotation period, the wobble period had gradually decreased. By late November, it had dropped to 7 hours. By early December, it was 6.7 hours and still decreasing. The trend was exponential, accelerating. An exponentially decreasing period implies exponentially increasing frequency, which in turn implies increasing energy input. Something was spinning up, ramping up its activity level, and the timeline pointed directly toward mid-December. For a mechanical system to increase its rotational frequency requires torque, a sustained application of force. For the anti-tail structure to wobble faster and faster would require either external torques, such as from asymmetric outgassing, or internal torques generated by active systems. The fact that the frequency was increasing smoothly and predictably, rather than erratically, suggested active control, a deliberate ramp-up toward some operational state. In engineering terms, this looked like a system approaching operational capacity. Gyroscopes, for instance, must be spun up to high speeds before they can be used for stabilization. Flywheels used for energy storage are charged by increasing their rotational speed. Communication systems often require calibration periods where components are powered up and tested before transmission begins. The accelerating wobble could represent any or all of these processes, systems coming online in preparation for a mission-critical event. Thermal observations added another layer to the picture. Infrared telescopes, which detect heat rather than visible light, began to observe unusual hotspots on the night side of the nucleus, the hemisphere facing away from the Sun. This was anomalous because the night side should be the coldest part of the object. Solar heating affects only the day side, and the night side, shielded from sunlight and radiating heat into the cold of space, should be significantly colder. Yet the infrared images showed localized warm regions, areas emitting more thermal radiation than their surroundings. The hotspots were not uniformly distributed. They appeared at specific locations and seemed to correlate spatially with the base of the anti-tail structure. Moreover, their intensity increased over time, growing brighter in the infrared as the wobble frequency accelerated. Heat on the night side of a comet has no natural explanation. There is no sunlight there to provide energy, and the thermal conductivity of ice and rock is far too low for heat to be transported efficiently from the day side. The only plausible source is internal, energy being generated or released within the nucleus itself and conducted or radiated to the surface. If the object were powered by some form of onboard energy system, whether nuclear, chemical, or something more exotic, periods of high activity would produce waste heat. That heat would need to be dissipated to prevent damage to internal systems, and radiators or heat exchangers would be necessary. In spacecraft design, thermal management is a critical concern, and large radiator panels are often required to shed excess heat, especially during high-power operations. The night-side hotspots could be radiators, surfaces specifically designed to emit infrared radiation and cool internal systems. Their increasing intensity would reflect increasing power consumption, consistent with systems ramping up for transmission or propulsion or whatever operations were planned. The power requirements for interstellar communication are staggering. To send a signal across light years and have it be detectable above the background noise of space requires enormous amounts of energy. Even using highly directional antennas and narrow beams, the inverse square law of radiation means that intensity falls off rapidly with distance. A signal that begins with a megawatt of power at the transmitter might arrive at a distant receiver with only femtowatts, quadrillionths of a watt, barely distinguishable from the faint hiss of cosmic background radiation. To transmit at such levels continuously for hours or days, as might be necessary to send a meaningful data package, would require hundreds of megawatts, possibly gigawatts. This is the output of a power plant, not a small generator. An interstellar probe operating on such a scale would need either a vast solar collection system or a compact high-density power source like a nuclear reactor, or even something more advanced, perhaps fusion or antimatter if we allow ourselves to consider technologies beyond our current capability. The evidence suggested that whatever power systems 3I/Atlas possessed, they were being brought to full output. Energy was being harvested from sunlight, stored in some form, and prepared for expenditure. The timing, again, pointed to December 19th. Then, in the second week of December, something extraordinary happened. The Deep Space Network, the array of large radio telescopes that NASA and other agencies use to communicate with distant spacecraft, detected an unexpected signal. The detection was brief, lasting approximately 8 minutes, and it came from a direction in space that did not correspond to any known terrestrial spacecraft or natural radio source. The direction was toward the asteroid belt, the vast region between Mars and Jupiter where millions of rocky and metallic bodies orbit the Sun. The signal's characteristics were unusual. It was highly coherent, showing a narrow bandwidth and stable frequency, and it exhibited modulation patterns that suggested structure rather than natural emission. Natural radio sources, such as pulsars or magnetars, have distinctive signatures that this signal did not match. It looked artificial. The detection was initially classified and not publicly announced, but within days, information began to leak into the scientific community. Researchers with access to DSN data logs noted the anomaly and began their own analyses. What they found was disquieting. The signal had been directional, not a broad broadcast but a focused transmission, and the direction of transmission, when traced backward from Earth's position, pointed approximately toward the location of 3I/Atlas. The timing ruled out certain possibilities. If the signal had originated from the galactic center region, the source of 3I/Atlas's interstellar trajectory, it would have taken tens of thousands of years to reach the solar system, given the vast distances involved. The galactic center is roughly 26,000 light-years away, meaning that even a signal traveling at the speed of light would take 26 millennia to arrive. No timing correlation with current events would be possible, but if the signal had originated much closer, from within our own solar system, then the travel time would be measured in minutes or hours. The asteroid belt, depending on the specific location and the relative positions of Earth and the source, is anywhere from a few light minutes to half an hour away. An 8-minute signal duration, combined with detection in the asteroid belt's direction, suggested a source at a distance of several light minutes, consistent with objects orbiting in the mid or outer belt regions. The implications were staggering. If 3I/Atlas were part of a coordinated network, if there were other components or relay stations already present in the solar system, then the object was not operating in isolation. It was part of an infrastructure, a communication chain designed to avoid the millennia-long delays inherent in direct transmission across interstellar distances. Consider the logic of such a system. If you wanted to send a probe to a distant star system and maintain communication with it, the traditional approach would be to build a very powerful transmitter on the probe and aim it back at the home system. But the energy requirements grow prohibitively large as distance increases, and there is no way to receive updated instructions or responses in less than the round-trip light travel time, which could be decades or centuries. A more sophisticated approach would be to deploy relay stations, intermediate nodes that receive signals from the probe, amplify them, and retransmit them toward home. This allows the probe to communicate with a nearby relay using much lower power, and the relay can then use a more powerful transmitter for the next leg of the journey. By chaining relays, you can extend a communication network across vast distances while keeping each individual link manageable. If such a relay were stationed in our asteroid belt, it would be perfectly positioned to communicate with objects in the inner solar system while also transmitting back toward the outer system and eventually interstellar space. Its location among millions of other rocky bodies would make it nearly impossible to detect unless it actively transmitted, and even then, distinguishing it from natural objects would require careful observation and analysis. The 8-minute signal detected by the DSN could have been such a transmission, a relay responding to a signal from 3I/Atlas and forwarding data toward the next node in the network. The fact that the detection occurred in early December, as 3I/Atlas was ramping up its activity, fit the timeline perfectly. Institutional responses to these accumulating anomalies were muted, almost suspiciously so. Major observatories and space agencies, which would normally issue regular public updates about significant astronomical discoveries, remained largely silent. Press releases were sparse and carefully worded, emphasizing the object's interstellar origin and its similarities to previously observed comets, while downplaying or omitting mention of the anomalies. Requests for telescope time to observe 3I/Atlas, submitted by independent research groups, were reportedly being granted at lower rates than expected given the object's uniqueness. Some researchers privately expressed frustration that their proposals were being declined or delayed, forcing them to rely on smaller instruments and less optimal observation windows. Meanwhile, much of the detailed data and analysis was coming from amateur astronomers and small research teams, observers operating outside the major institutional frameworks. Their findings were being published in online preprints and discussed in forums, but they were not receiving the prominent coverage or official validation that would normally accompany discoveries of this magnitude. This pattern suggested either bureaucratic inertia and caution, institutions moving slowly and waiting for more data before committing to controversial conclusions, or something more deliberate. If the implications of the observations were being taken seriously at high levels, there might be concerns about public reaction, about the social and geopolitical consequences of announcing that an artificial object from another star system was currently active in the inner solar system. Information control, whether for reasons of security or simply to avoid premature conclusions, could explain the relative silence. Whatever the cause, the effect was that the most dramatic findings remained confined largely to the scientific community, discussed in technical papers and specialist conferences, but not widely disseminated to the broader public. As December progressed and the 19th approached, attention focused on the object's trajectory. Orbital mechanics, the mathematics governing motion under gravity, allow predictions of future positions with extraordinary precision. For 3I/Atlas, the calculations had been refined to high accuracy through months of continuous observation. The trajectory was becoming more precise over time, not less. This was counterintuitive. Natural comets, as they outgaze and shed mass, experience non-gravitational forces that perturb their orbits in unpredictable ways. These perturbations accumulate, making long-term predictions increasingly uncertain. Observers typically see trajectories becoming less precise as more data is gathered and the cumulative effects of outgassing are included in models. 3I/Atlas showed the opposite behavior. As more observations were added, the orbit solutions converged rather than diverging. The uncertainties shrank. The predicted position for December 19th and the days following became more and more exact. This suggested that the non-gravitational forces, whatever their source, were not random but controlled. The object was adjusting its trajectory, making small course corrections that maintained a specific path rather than drifting chaotically as outgassing jets would cause. The refined trajectory showed that the object would pass Earth at a distance of approximately 60 million kilometers, well outside the orbit of the Moon, but close enough in astronomical terms to be considered a relatively near approach. The flyby would occur with a relative velocity of several tens of kilometers per second, fast enough that the encounter would be brief, measured in days from closest approach to departure back toward interstellar space. But the precision of the approach was remarkable. Among the countless possible trajectories that an interstellar visitor could follow, entering the solar system from a random direction with a random velocity, the path of 3I/Atlas brought it through the inner system at a time and angle that created optimal conditions for observing Earth. It would pass sunward of our planet, giving it a clear view of the day side, and the timing placed it at closest approach during the December 19th alignment. Natural trajectories do not optimize themselves for planetary encounters. The chances of an interstellar object arriving randomly from the galactic disk, happening to pass near Earth at a specific date and angle would be extraordinarily small. But a planned trajectory, one designed to bring a probe into the inner system for reconnaissance, would look exactly like this. You would aim for the habitable zone, the region where liquid water and life are possible. You would time your arrival to create favorable geometry for data collection and transmission. You would make small adjustments en route to refine your approach as conditions changed. The implications of the trajectory were clear, even if unstated. This was not a random flyby. It was an intentional approach, a close encounter designed to gather information about Earth while maintaining a safe distance. Whether safe meant safe for the object, avoiding collision or excessive gravitational stress, or safe for Earth, avoiding any disruptive close approach, was an open question. And this led to the final, most unsettling questions. What would happen after the flyby? There were 3 broad scenarios, each with different implications. The first scenario was the simplest. The object could complete its flyby, transmit whatever data it had collected, and depart. It would swing past the Sun, using the star's gravity to bend its trajectory and add velocity through the Oberth effect, and then climb back out of the solar system, accelerating onto an outbound hyperbolic trajectory. Within months, it would cross the orbit of Jupiter. Within a year, it would be beyond the orbit of Saturn. Within a few years, it would exit the heliosphere and return to interstellar space, carrying its observations back toward its origin across the long decades or centuries of travel. This outcome would be anticlimactic in some ways, leaving humanity with a wealth of data and mysteries, but no direct interaction. We would have been observed, catalogued, perhaps communicated with in ways we did not fully recognize, and then left alone. The visitation would join the ranks of historical enigmas, debated and analyzed, but never definitively resolved. The second scenario involved a parking orbit. If the object were to make even a small adjustment to its velocity at the right moment during the solar flyby, it could shift from a hyperbolic, escape trajectory to an elliptical, bound orbit. This would not require a large maneuver. The difference in velocity between a hyperbolic and an elliptical orbit at perihelion, the point of closest approach to the Sun, can be as little as a few hundred meters per second, well within the capability of any propulsion system capable of producing the observed anti-tail. Once in a bound orbit, the object could remain in the solar system indefinitely, swinging through the inner system at regular intervals or settling into a long-period elliptical orbit that kept it in the outer system most of the time, returning to the inner regions only occasionally. This would allow extended observation of Earth, monitoring our development over years or decades. It would transform the visitation from a brief encounter into a permanent presence, a silent observer stationed in our cosmic neighborhood. The third scenario was the most speculative but also the most profound. If the object were operating under instructions, if its behavior were governed by a mission plan that included contingencies and decision points, then the outcome of the flyby might depend on what it observed. If Earth's technosignatures, the radio emissions, the atmospheric composition, the artificial lights visible from space met certain criteria, the mission could shift to a new phase. Secondary objectives could be activated. This might involve attempts at direct communication, signals specifically directed at Earth in formats designed to be recognizable as artificial. It might involve deployment of sub-probes, smaller craft released to enter orbit around Earth or other planets for closer observation. It might involve altering the trajectory in unexpected ways, moving to positions that allowed more detailed study. The nature of such responses would depend entirely on the purpose of the mission and the level of sophistication of the systems involved. A purely scientific probe might behave differently than one designed for reconnaissance in anticipation of contact or expansion. The possibilities ranged from benign curiosity to strategic assessment, and without more information, any speculation was just that. What was clear was that December 19th represented a convergence. The geometric alignment, the system ramp-up, the trajectory refinements, the increasing wobble frequency, the thermal anomalies, all pointed to that date as a moment of significance. It was not an end, but a beginning, the transition from passive observation to active operations. Humanity, for its part, was largely unaware. Beyond the specialized communities of astronomers, planetary scientists, and aerospace engineers, 3I/Atlas remained an obscure footnote, a curiosity mentioned occasionally in science news but not widely discussed. The public's attention was elsewhere, focused on terrestrial concerns and the daily flow of events. Even among those who followed space news, the object was often described in conventional terms, as an interstellar comet making a rare visit, unusual but explicable within the bounds of natural phenomena. But for those who had followed the observations closely, who had seen the data accumulate and the patterns emerge, the picture was impossible to ignore. This object was not behaving like a comet. It was not passive. It was not chaotic. It was not random. It was executing a plan that had been set in motion long before its arrival, perhaps decades or centuries ago when it was launched from a distant system and aimed toward this unremarkable yellow star in a quiet arm of the galaxy. It had crossed the void between stars, traveling through the cold and dark for time spans that dwarfed human history, and it had arrived precisely on schedule. Its systems, dormant during the long journey, had awakened as it entered the solar system. Power systems had come online. Propulsion had been tested and activated. Communications arrays had been deployed and aligned. Data collection had begun. Sensors gathering information about the Sun and planets, about the composition of the inner system and the characteristics of the third planet from the star, the blue-green world with its oxygen-rich atmosphere and its electromagnetic noise, signs of technology and life. And now, as December 19th approached, the object was preparing for the critical phase of its mission. Whatever it had been built to do, whatever questions it had been sent to answer, The moment was at hand. The geometry was optimal. The systems were ready. The transmission window was opening. For those watching, the hours and days ahead would bring either confirmation or confusion. If the object were truly artificial, if it were truly executing a mission plan, then December 19th should bring observable changes, new behaviors, perhaps signals that could be detected and analyzed. If the interpretations were correct, humanity was about to witness something unprecedented: contact with a technology from beyond our solar system, evidence that we are not alone and that others have been watching. And the object itself, silent and dark, moving through space with its impossible anti-tail glowing faintly against the black, approached the moment that everything had been leading toward. The wobble accelerated. The hot spots brightened. The trajectory held steady, refined to precision. Somewhere in the asteroid belt, if the relay hypothesis was correct, another system waited, ready to receive and forward signals across the chain, out past the Kuiper belt, past the heliopause where the solar wind fades into interstellar medium, and onward across the light years toward a destination we could only guess at. The plan had been in motion for longer than we knew. The preparation had been thorough. The execution was unfolding with the inevitability of orbital mechanics, forces, and trajectories that had been calculated long ago and were now simply playing out as designed. Humanity had been discovering comets for thousands of years, charting their paths, predicting their returns, understanding their nature. We had become comfortable in our knowledge, confident that we understood these icy visitors. But now, as 3I/Atlas approached its closest point, as December 19th arrived and the alignment became exact, that comfort was eroding, because this was not a discovery in the traditional sense. We were not finding something that had been waiting to be found. We were not uncovering a secret that nature had hidden. We were being discovered. We were the object of observation, the subject of study. Our techno-signatures, the unintentional broadcasts of our civilization, had been detected from light years away, and something had been sent to investigate. It had traveled for decades or centuries, crossing the incomprehensible distances between stars, and it had arrived. The plan had always been to reach Earth. The plan had always included this moment, this date, this alignment. What we were witnessing was not improvisation. It was not malfunction. It was not natural phenomenon misunderstood. It was the unfolding of intention, the execution of purpose. The object knew what it was doing. It had known from the beginning. And as the clock counted down toward December 19th, as the alignment approached and the systems reached full operational capacity, the question that hung in the air was not whether something would happen. The question was what we would do when it did. Because the moment of activation was not the end of the story. It was the beginning of something else entirely, something that had been planned long before we were aware of the plan. Something that was about to unfold according to a design we had not written and could not control. The plan began long before us, and it was about to unfold.